Hello and welcome to this Edexcel Statistics 1 video, Introduction to the Geometric Distribution. If we just consider the binomial and geometric distributions, in the binomial distribution you have been used to the fact that there are a fixed number n of independent trials and a constant probability p of success at each trial. And if y is the number of successes in n independent trials, y follows a binomial distribution with parameters n and p, and the possible outcomes are y equals 0 up to a maximum of y equals n. With the geometric distribution, the only parameter is p, the constant probability of a success, and if x follows a geometric distribution, x represents the number of independent trials necessary before the first success occurs. And note that the first value x can take is 1, and that's because we need one trial before we can have one success. The geometric distribution involves two mutually exclusive outcomes, as you've met with the binomial distribution previously. This discrete distribution has one parameter p, the probability of a success, and the possible outcomes are discrete and start at the value x equals 1. So to summarize here, with the binomial distribution we have a fixed value of n, but for the geometric distribution there are no fixed number of trials. The binomial has a finite number of possible outcomes. With a geometrically distributed variable, there's a theoretical infinite number of possible outcomes. If you like using GeoGebra, then you will find in their probability section that binomial and geometric distribution probabilities are available, and you can plot several using a slider for n, and obviously n only applies to the binomial, but as long as it's sufficiently large it won't affect the geometric probabilities. And try it out for different values of p, and you'll see the symmetrical nature of the binomial distribution, which is the distribution in red at the top, for values of n even from 10 upwards, provided p isn't too extreme. And you can contrast that with the blue probabilities below for the geometric distribution, where you'll see that the distribution is very much skew and not symmetrical. So if we have a look at the binomial and geometric distributions, there's a couple of examples here and you might like to pause for a moment to read them through. Example A, the variable is the number of children born into a family before the first male. Clearly no fixed n. The probability of a success of getting a male child in this case would be a half, so that could be modelled by a geometric distribution with probability a half of success. Whereas if we look at B, we clearly have a fixed number of children in our family, and the variable we're interested in is the number of males out of 5 children. So again, the probability of success of getting a male is a half, so the variable, if we call it y in this case, would follow a binomial distribution with parameters 5 and a half. So here we have a few more examples of geometric distributions. The first example, how many friends must be asked in order to find the first one to guess the day of the week on which her mother was born correctly. Now we don't know how many, so there's no value for n, no fixed number of trials, but we do know the probability of guessing one day out of 7, correctly is going to give us our constant value for p, and so this would follow a geometric distribution with probability 1/7. The second example, very straightforward. How many times must we flip a coin? So geometric distribution. The probability of success is the probability of a tail, so that's a half. So that would follow a geometric distribution with probability a half. And the third example here, slightly more modelling assumptions required here. How many people must be selected and asked until we find a person who attended the last Everton home game? And we are given the information that we can assume the probability of a person attending the last home game is 0.2. So again, this could be modelled with a geometric distribution, probability 0.2. So if we just look at a simple example here, just one probability, and find the probability the third child is the first male. So the probability of a success is going to be 1/2, and therefore the variable involved is going to be geometrically distributed with probability a half, and we want to work out the probability that x equals 3, that we need to get to 3 children before we have our first success, our first male. And that, following the probability function that you looked at before, would be p multiplied by 1 minus p to the 3 take away 1. So we're having 1 success, 2 failures prior to that. So very simply here, that's a half. 1 minus a half squared, that's going to give us a half, all cubed. So the probability is 1/8 or 0.125. And you might like to compare that with what you could do with a tree diagram in order to evaluate that very same probability. So we have 3 children here, first child, second child, third child. Each child could be male or female. If we add on there the probabilities, obviously a half on each occasion and for male and female. So if we look at the outcomes now written onto the tree diagram, we want the third child to be a male, so it's only these outcomes that are feasible, but we want it to be the first male, so that child's the third male, this child's the second, this child's the second male, and the only branch that gives us what we want is this one, 2 girls and a boy. And if we look at the probabilities, the probability of that event is going to be a half multiplied by a half multiplied by a half, or 1/8, which is exactly what we obtained using the geometric model. That's the end of this video. The next video will be on calculating probabilities from the geometric distribution, looking at slightly more tricky examples than we have done today.